So today we are going to solve the questions from this chapter, all the examples, all the solved questions, all the questions for short answer, objectives, and the exercises. So stay tuned with me. I'll be solving and explaining you. So generally, the solved examples are given. You can read and understand, but with me, if I solve it, I will give you a different understanding of things. A better understanding of things, to be precise. So these questions are simple. The first questions are simple. So it is given that the spring is of a spring constant 50 Newton per meter, and it is compressed through 1 centimeter. Then the work done by spring force on the agency compressing the spring. So you can see that the K given is 50 Newton per meter, and it is compressed by a distance 1 centimeter, which is equals to 0.01 meter in SI units. So work done by spring force is half K x1 square minus x2 square. So we have seen that x1 square is initial position. So the initial position is natural. So let us say that the natural position is 0. Then it says that the spring force on the compresses the spring. Compresses the spring means, suppose initially it is like this. This is the natural position. Then it compresses and the box comes here. So this distance is 1 centimeter. So because it is in the negative x direction, let's take it minus 0.01 meter. Now this is equals to half K. K is 50. So let us write it as 50. And x1 square is 0, 0, and minus x2 square. So this is minus, and 0.01 square is 0.0001. So this becomes minus 0.0025 joule. And answer is similar. It is given in notations. So it is 2.5 into 10 to the power minus 3 joule. If you multiply it by 3, it will be 2.5, and that is how this notation is there. Now in this example 8.2, it is given that the particle has mass 20 grams and it is thrown vertically upwards with a speed of 10 meter per second. So this is the initial speed. So the work done by force of gravity during the time the particle goes up. So here is the particle is thrown up, and it is asking the work done by the force of gravity during the time the particle goes up. So the time where it goes from point A to the highest point B, and we know that at the highest point velocity will be 0. So let us see what we can do. So suppose at highest point velocity is 0, and we know that the mass given is 20 grams, which is equivalent to 20 by 1000, that is 0.02 kilogram. 0.02 kilogram. And initial velocity is 10 meter per second. So we know that final velocity will be is equals to 0. So let us use equations of motion. So v square is equals to u square plus 2as. Now here acceleration is equals to g, which is in the downward direction, and h is above, which is in the positive above direction, positive direction. So this thing will become minus. So let us write that u square minus 2g h s equals to distance is, let us write distance as h, and since v is equals to 0, this thing becomes 0. So and u square is 100, so this becomes 2g h equals to 100, and h equals to 100 by 2g. So if we take g is equals to 10, then this thing becomes 100 by 20, this thing becomes 5. It means the ball ascended a distance of 5 meters. So work done by gravity, what will be the work done by gravity? The ball is here, the gravity is acting downwards, and the ball is moving upwards. So it is in the opposite direction, which means theta equals to 180 degrees, which means cos theta is equals to minus 1. This is mg, force is acting downwards, and the ball is moving upwards the distance, and we know that the work is equals to force into force into distance into cos theta, fs cos theta. So cos theta is minus 1 here, cos 180 is minus 1, since they both are acting opposite, and force is m into g, and distance is traveled is 5 meters. So force is m into g, m is 0.02 into 10, and the height it ascends is 5 meters into minus 1. So this whole thing becomes minus, this is 0.2 into 5, this becomes 1. So this whole thing becomes minus of 1 joule. Now this example 8.3 is an interesting example. We will see how this works. We will use many concepts here. So it says that there are two charged particles, A and B, both are charged, and they repel each other. And that force of repulsion is K by R square, where K is constant and R is the separation between them. The particle A is clamped to a fixed point. It is fixed, and particle B has a mass m, and it is released from rest with an initial separation r0 from A, and since they both repel each other, uh, A will try to throw B away from its place, and it will increase the distance. So in order to understand that, we need to find change in potential energy of this A and B system as the separation increases to a large value. So what will be the speed of particle B? So it says that there is some particle A. This particle A is hinged, is clamped, it is fixed, and there is some particle B. So this is B and this is A. A is clamped. So what are the type of forces acting here? First, let us understand that. So there is definitely a force of repulsion between A and B. The B is applying certain force on A. So let us say that force on A due to B, and force on B due to A. What are the other forces here? The other forces here, the external force here is this clamp, which is holding A in place, is a force which holds A in place. And but this force is not doing any meaningful work because there is no movement due to this force. It is working on A, and A is fixed, A is not moving. So according to our definition of work, no work is done. So this force is not doing any work in this system. So if there is no external force, F external is equals to 0, or either say that work done by external force is equals to 0, then the system then the system only has internal forces, and these internal forces are conservative. These internal forces are conservative. What is the internal force acting here? The internal force acting here is force is equals to K by R square. That is the internal force. Internal force. And we have studied if there is no external force and only internal conservative force acts, then the total mechanical energy remains constant. If internal force and this internal force is conservative. If you don't know what is conservative, you can go and look into the theoretical lecture class. Conservative basically means that the work done depends on initial and final position, does not depends on the path taken. And if it is a circular path, if the object goes from A to B and back to A, then the work done will be 0, since the initial and final position is 0. So that is it. So here we can say that since internal conservative forces act, so total mechanical energy is conserved. Conserved. So here we can write that the work done by this force, this internal conservative force, the force which is acting to repel A and B, is equals to integration of F bar dot dr bar, which is equals to, the integration will work, the initial separation is r naught, and maybe whatever up to infinity wherever it goes. So F is K by R square and dr. So we will take K outside, and integration of R square is R, 1 by R. So this thing becomes K into 1 by infinity minus 1 by R naught. So this whole thing becomes, so this thing here was already minus 1 by R. Integration of 1 by R square will be minus 1 by R. So this is minus 1 by infinity plus 1 by R naught. Since minus 1 by infinity will be 0, so this thing becomes K by R naught. Now, what will be the change in potential energy? Now we are coming to the second concept, what has been asked. First we calculated the work done by that force. Now we will see what is the change in potential energy due to that work done. So we know that change in potential energy is defined as UF minus UI is equals to minus of work done. So we want change in potential energy. So this whole thing we will want it as it is. We say that minus W is equals to, and W is K by R naught. So this becomes minus K by R naught. This is step 1. This is step 2. Now we know that the total mechanical energy remains conserved. So in order to say this third step, we will do total mechanical energy is conserved, which means that final kinetic energy plus final potential energy is equals to initial kinetic energy plus initial potential energy. So we can write Kf is equals to Ki plus Ui minus Uf, which can be written as Ki minus Uf minus Ui. Now this initial kinetic energy is equals to 0 as there is no velocity initially, because the particle B was brought near it and initially it was at r0 distance. So initial separation was there and it was released from rest. So now this thing becomes Kf. We can write Kf as like that half mv square is equals to K by r0. This thing is K by r0. This thing is K by r0, as uf minus ui is minus K by r0 and this is minus, so minus into minus plus K by r0. So we can write v square is equals to K by r0 into m and 2 at top. So velocity is equals to under root 2k by m r0. So this is the answer for the second part. What will be the speed of the particle B? The speed of the particle B will be V is equals to under root 2k by m r0, and change in potential energy will be equals to minus K by r0. So we need to understand how we have to approach these type of questions where multiple concepts are being used. This is one of the very good questions where we used almost all the concepts we studied. First we calculated work from the integration formula. Here we calculated it from r0 to infinity, the total work done. And then we calculated the change in potential energy based on this work. And then based on the mechanical conservation law, we calculated the kinetic energy and then we calculated velocity from it. Now here we are given a block. This block is of mass m. This block is of mass m and it reaches from A to B, this position B, and the height is h, and this will be some distance, and this is a frictionless surface. So what happens if it is released from rest? Then what will be its speed when it reaches B? Speed at B, and the surface is frictionless. So how do we analyze this? So first of all, we will see what are the type of forces here. So suppose when the box reaches here, what will be the type forces acting here? One will be the force due to gravity. There can be force due to friction, but since it is frictionless surface, friction force is equals to 0. It is moving downwards. So there will be components of velocity, components of gravitational force, and there will be a normal reaction force. The normal reaction force throughout its journey works perpendicular to the movement, and hence work done by normal is equals to 0, because normal is perpendicular to the distance traveled by the object. So we can say that the only force acting here is mg, or the gravitational force. So since only gravitational force is acting, and we know that it is a conservative force, it is an internal force, then we can say that no external force is acting on the system. So the mechanical energy is conserved. Mechanical energy is conserved means kinetic energy final plus potential energy final is equals to kinetic energy initial plus potential energy initial. Now here kinetic energy final will be something because it will have certain velocity when it reaches down. But what will actually happen to potential energy when it reaches down? It is at a height h, and when it descends to a height 0, it will be on the level of the ground. I mean, it will be on the level of the ground, that is height h will become 0. If h will become 0, the potential energy, or the potential energy due to the height, will become 0, as it is mgh, and h is 0, so this will become 0 here. So u final is equals to 0, so this thing gets cancelled out. Now what is the kinetic initial? We know that initially it is at rest, it is released from rest. So if it is released from rest, kinetic energy is also 0, which means we will be doing kf is equals to ui. So when we are solving questions in examination, we need not do this. We will develop an understanding. We will understand that if it is released from rest and it gains some velocity and no other force is acting, it means it is gaining velocity due to the loss in the potential energy, due to the loss in the gravitational energy of the system. So kf is equals to ui. So what is kf? Kf is equals to half m v square, and ui will be is equals to mgh. So our now here m gets cancelled, so v square is equals to 2gh, and v is equals to under root 2gh. So the mechanical energy remains conserved, and when the object is moving down, so suppose the object is here at this point and this is some height h1, then it will have certain velocity here, and it will have the the potential energy will be mg h1. So, and in that case also, the sum of mg h1 plus kinetic energy at that point, suppose this is point 1, then kinetic energy at point 1 plus potential energy at point 1 will be is equals to constant, and this will also be is equals to at final the sum of kinetic and potential at final and the sum of kinetic and potential at initial. So I have explained it all in detail in the theory classes. Now we are coming to an interesting question of bob and pendulum system, the example 8.5. So it says that there is a pendulum bob which has a speed of 3 meters per second while passing through its lowest position, and it is asking us to find the speed when it makes an angle of 60 degree with the vertical. 60 degree with the vertical, and length is given, and g is equals to this. So suppose this is the ceiling, the bob is connected here. Now the bob moves, and bob reaches certain point here. Initially the velocity at this position, velocity, suppose this is a, so velocity is at a is 3 meter per second. This is the lowest position, and now it reaches somewhere here where it makes an angle 60 degree with the vertical. This is the vertical, it makes an angle 60 degree. So now again here no external force is acting. F external is equals to 0. Work done by external is equals to 0. Again here only internal forces are acting, internal conservative forces, which means that total mechanical energy is equals to conserved. Total mechanical energy is conserved, which means that K plus U is equals to constant. Kinetic energy plus potential energy equals to constant. So here we do kinetic energy initial plus potential energy initial is equals to kinetic energy final plus potential energy final. Now what happens at kinetic energy? What is the initial kinetic energy? We know that the initial velocity u is equals to 3 meter per second, which is also velocity at a. I mean this is same thing. So ki is equals to half m v a square, because that is our initial position, plus what is initial potential energy? Potential energy here is 0, because this is the lowest most point, and let us take potential at a point is equals to 0. We know that we calculate potential based on some other previous value. That is why potential energy is always defined as some joules more than the previous value or less than the previous value. It is a comparative term. So let us say that at a potential energy is equals to 0. It is 0 here, becomes 0 is equals to what is kinetic energy final. So here it will have some velocity, v, say it is vb, it is v point, so it will be half m v b square plus what will happen to potential energy. We know that it will have some potential energy which is mgh. It has gained some height, but what is that height? We will have to calculate that. How do we calculate that? Suppose uh, it reaches this height. So in the vertical distance, it has traveled this much. So for mgh, in order to calculate mgh, we need to find this height. From A to B, we need to find AB. We know that this length is L. This length is L. L is equals to length of the string, which is equivalent to 0.5 meter, which has been given to us. And this is L cos 60. So this thing from here up to here, this becomes L cos 60. And this whole thing, this total A to the initial position, this whole thing is L. So this thing becomes L minus L cos 60. So the distance traveled is L minus L cos 60. Now let us calculate. VA square is equals to 9. So this becomes, and we have not been given mass. Okay, so this becomes 9 m by 2 is equals to half m vb square. We have to find, actually we have to find vb. So it becomes m vb square by 2 plus mg. We are supposed to take g equals to 10. So it becomes 10 m L into 1 minus cos 60 and L into 1 minus cos 60. So this becomes m into 9 minus vb square. This thing goes that side. 9 minus vb square by 2 is equals to 10. L is 0.5 meters, so 10 into 0.5 becomes 5. So this becomes 5m into 1 minus cos 60. What is 1 minus cos 60? 1 minus cos 60 is equals to 1 minus cos 60 is 1 by 2, 1 by 2, which is equivalent to 1 by 2. So this is 1 by 2, so this becomes 5 by 2. 2 gets cancelled. Now m and m gets cancelled, 2 and 2 gets cancelled, so it comes as 9 minus vb square is equals to 5. Is vb square is equals to, vb goes that side, 9 minus 5, which is 4. So vb is equals to 2 meter per second. So what do we understand? Here the velocity was 3 meter per second, and in raising to that height, the height is 1 by 2 meter. In raising to height 1 by 2 meter, the ball, the system, the bob and string system loses its velocity and it becomes 2 meter per second. And one more thing to consider here, to understand from this whole thing, is that this thing is independent of the mass of the bob. It is only depend, the velocity at B will only depend on velocity of A, no matter the mass of the bob, because the mass thing is getting cancelled. I mean, it seems a bit arbitrary, but it is the case. The mass is getting cancelled, and so the velocity does depend only on the initial velocity at A. Now in this new question we have, there is a block of mass m, and this block is attached to a spring, and which has a spring constant k, and it oscillates on a smooth horizontal table, and smooth, which means friction is zero, no friction is applicable here. So, and the other end of the spring is fixed to a wall, and if it has a speed v at its natural length, how far will it move on the table before coming to an instantaneous rest? So it is something like this. This is a horizontal table. Now, what will be the kind of forces which will act here? First of all, mg will act downwards. There will be a natural force, a natural reaction upwards, and there will be some force of the wall, because the spring is clamped here, spring is fixed here. But natural reaction force and mg perpendicular to movement, so work done by them is equals to 0, and force by this wall, work done by wall is equals to 0, because distance is 0. Due to that force, here nothing is moving. So we are back to only internal conservative force, which is spring force. Spring force is an internal conservative force. So we can easily do here, either we can do kf plus uf is equals to ki plus ui, as we did in previous question, but it will have no bearing. We will understand that. Okay, we are being told that finally it will come at rest. It means kinetic energy is 0. And what will be the potential energy? Here there will be two kinds of potential energy. That is why I wrote it like this. We know that potential energy is for every type of conservative force. We can define potential energy for conservative forces. So here we can define potential energy for gravitational force plus potential energy for spring force. Now what will happen to the potential energy of gravitational force? Since there is no change in height, it is a horizontal surface, and even if it is spring is compressed or elongated, it remains on the same height from the ground. So the potential final and potential energy is same. So potential remains same. Potential of due to gravity remains same. However, spring potential changes with change in distance. We will see how this happens. This will be based on half k x square because that is the work done, and we know that potential is minus of work done. So we understand all that. So UF, we can write it as half k x square. Finally, it is moving to a distance x. Some distance, it is moving some distance. Let us call that x. And kinetic energy initial is equals to half mv square. And potential energy initial is equals to 0. And why is it 0? Because initially it is at natural length. Spring is at its natural length. So at natural length, potential energy is equals to 0. Why? Potential energy is defined as half k x square, and at natural length we take x is equals to 0. So this whole thing becomes 0. Now half gets cancelled, and we can write x square is equals to mv square by k, and we can write x equals to v under root m by k. X equals to v under root m by k. So that is it. It was asking what will be the movement of the block. So it will move a distance x, which is equals to v under root m by k. Now this is a very important question which will form the basis of whatever we are going to do further now. All the exercise questions and all that, this will be the base of all of it. Earlier all the questions we solved were to brush up our theoretical knowledge. It was not so heavy on the numerical part. Now this is somewhat heavy and will form the basis of whatever is to come ahead. So it says that there is a block of mass m which is suspended through a spring of a spring constant k and is in equilibrium. Equilibrium means it is not moving. It is at the equilibrium in this context means it is not moving. It is at rest now in this when the mass is suspended through that spring condition. So a sharp blow is given to the block in downward direction, initial downward velocity v. So how far below the equilibrium position will the block come to an instantaneous rest? So what it says is, suppose there is this spring and a block of mass m is attached to it, and now it is somewhat stretched from its natural position. It is not at its natural position, but it is in an equilibrium position. It means it is at rest now, it is not moving, and we apply a sharp blow downwards. Apply a sharp blow downwards, then it moves certain distance, certain height, it descends certain height and reaches this position. Suppose this height of descent is h. It moves down, and here at this position, suppose let us say this is position A and this is position B. So at this position the velocity becomes 0. We can also understand this that if the spring is stretched to a maximum point, the velocity at the maximum point is 0, and then it will start getting back towards its natural position. So here, what do we need to understand is, in its equilibrium position at A, so let us say at A, what happens at A? At A, gravity is acting and tension force is acting upwards. But here, this tension is not some uh, common thing. This tension is the spring force. So this tension is equals to Kx, which is equals to mg, because it is in equilibrium position. That is what equilibrium position meant. So we can write Kx equals to mg. So in doing so, we find the elongation, the initial elongation in the equilibrium position. That is mg by k. What is this elongation? This elongation is that when the block of mass m is suspended from that spring, it is stretched to some point. It is not moving, but it is stretched to some point. So that it is stretched by length x from its natural position. So that stretching is x equals to, that elongation in the spring is by distance x is equals to mg by k. Now we know that in the same equilibrium position at A only, what will be the total potential energy of the spring? Total potential energy of the spring is equals to half k x square is equals to half k mg by k ka whole square, which is equals to k square is down, which becomes m square g square by 2k. This is the potential at A. This is the spring potential at A. We also know that there is a gravitational potential. So let us take gravitational potential at A is equals to 0, because we know that again that potential energy is considered or calculated from some previous position or some previous point. So that point for us at position A, let us say that it is 0. The gravitational potential energy is 0. We assume that we can assume it anywhere, and then based on height we will see that right now. So here no external force is acting. The only force acting is the gravity and the spring force. Both are internal. One external force which is acting is the force of the ceiling on the spring. The spring is hinged to the ceiling and ceiling is holding it in place, but it will not do any meaningful work because the spring is at its place. Spring is elongating, yes, but the initial position of the spring from where it is hinged to the ceiling is not changing. So the work done by the external force, the ceiling force, is equals to 0. Hence only internal forces remain. So we can apply the conservation of total mechanical energy here also. So what will be the uh, total mechanical energy at A? Total mechanical energy at A is equals to sum of kinetic energy and potential energy. So what is the sum of kinetic energy here? Suppose at A only a blow was given to it and it acquired a velocity v. So it's let us think of it as just a bit after A. If the velocity is applied just a bit after A, what happens? If the force was applied just a bit after A, and then half m v square. Although initially at A the velocity was 0, it was at rest, but a blow was given, an energy was given in the downward direction for it to gain certain velocity. And finally, the spring comes to rest. So in order to calculate it, we consider it that just a bit after a, it gains the velocity v, and we are taking that velocity at a only for our calculation purposes. We are going to do this a lot, so we need to understand the mathematics of this. So this is half mv square plus potential. So this potential will be sum of potential of a spring plus potential of g. So here only potential of a spring is there, which is m square g square by 2k. Now our system reaches B. What happens at B? At B, it will have certain velocity. That velocity will be is equals to 0 because it comes at rest. We are finding the what happens when the block comes to an instantaneous rest. The block comes to the rest when it has reached, when the spring has reached its maximum elongation. So that maximum elongation we are taking as h. So now we will calculate the sum of potential energy and kinetic energy at B. So first let us see that what is the spring potential at B is equals to half k x square. So it was x square initially. Now what is the x here? Now x here is x plus h. It was x at A and it has gained some height h. It has gained some distance. I mean, not actually gained, it has descended to a distance h. So more potential will be there. So we can write it as half k mg by k, x is equals to mg by k plus h whole square. Now, what happens to the gravitational potential energy? It becomes mg minus h. Since it has descended, so it becomes minus mg h. Now, what will be the kinetic energy at this state? Kinetic energy at B is equals to half m vb square, but vb is equal to 0, so this becomes 0. Now let us use our equation, conservation of mechanical energy equation. Let us use that equation. So that becomes kinetic energy final is equals to kinetic potential energy plus sum of potential energy and kinetic energy at final position is equals to sum of potential energy and kinetic energy at initial position. So here we have already done that. So we can say that TMEA. So what is total mechanical energy at B is equals to half k mg by k plus h whole square minus mgh. So we need to equalize that, which is equals to total mechanical energy at A is equals to total mechanical energy at B, which is half mv square plus m square g square by 2k is equals to half k mg by k plus h square minus mgh. Now on solving this, we will solve this. So what will come? The answer will be h is equals to v under root m by k. So height will be equals to m under root v under root m by k. So in the last question also we saw that when the spring was given a horizontal push, in the horizontal direction also, the distance moved was x is equals to v under root m by k. And here also the distance moved even in the vertical direction is m by k. In the last question, our question was when the block is there and some force is applied and it is moving, it moved to a certain distance and came to rest. And then what is the x? What is the distance it traveled in the horizontal direction? And that was also x equals to v under root m by k, where v was initial velocity and mass of the velocity. M was mass of the block and k was the spring constant. So we need to understand this. We don't need to solve the questions in vacuum. Each and every question is related to each other. When we are solving HC Verma, each and every question is related to each other. If you are able to solve a question, then you will be able to solve the next one very easily. So it means we can conclude that either for vertical or for horizontal distance, if an initial velocity v is applied to the spring block system, then the distance it will travel will be is equals to v under root mass upon spring constant. So for solving questions in examination, you need to remember this. You can remember this. Important. H equals to v under root m by k. This will make your life easy because otherwise you will have to discuss all this and you will have to solve all this. Now we are solving worked out examples which are already given in the book, which are solved examples. And I will explain to you how to do this. Um, After what I will explain to you, you may not need to refer to the book about these questions. You still need to refer to the book about the theoretical part, but you even if you don't refer to the book about these questions, I will explain it enough. So a potter lifts a suitcase weighing 20 kg from the platform and puts it on his head 2 meter above the platform. Calculate the work done. So we know that mass is equals to mass is equals to 20 kilogram and a height is equals to 2 meter. And let us say g is equals to 10 meter per second square. So in taking the suitcase on his head, the suitcase will have a force downwards, that is mg, which is equals to 20 into 10, which is equals to 200, and it moves up to a height above for 2 meter, and mg and h both are in opposite direction. So for opposite direction, it means theta is equals to 180 degree, which further means cos theta is equals to -1. Cos 180 is equals to -1. So work done is equals to F into distance cos theta. So here F is 200, distance is 2, cos theta is -1. So it becomes minus 400 joules. So around 400 joules of energy is spent by the porter in lifting a suitcase of 20 kg onto his head, which is 2 meters above the ground. So here an elevator weighing 500 kg is to be lifted up at a constant velocity. So mass of elevator is 500 kilogram and it is to be lifted up at a constant velocity of 0.20 meter per second. So what would be the minimum horsepower of the motor to be used? So we know that 1 horsepower is equals to 746 watts. So what do we need to do here? What are the things we know? So since it is asking for us to find the minimum horsepower, so it means that it is asking for us to find the power. Power is equals to what? And what is power? Power is equals to work done per unit time. And what is work? Work is force into distance upon time. So we can write it as force into velocity. Now there is an we have already discussed this equation, but again let us discuss this. So what will be the force? Force is mg, as the gravitational force is acting on the elevator. This is the elevator and gravitational force mg is acting on it, which is equals to 500 into 10. We are taking g is equals to 10 meter per second square. So this becomes 5000 newtons into velocity. What is velocity? 0.20 meter per second. So this is 5000 into 0.20, which is 2 into 50, which is 100 watts, which is equivalent to 0.2, which is equivalent to 1000 watts. Now we know that 1 horsepower is equals to 746 watt. So 1 watt is equals to 1 by 746 horsepower, which is equivalent to, so for this equation, this thing becomes 1000 by 746, which is equals to 1.3 horsepower, approximately is equals to 1.3 horsepower. Now this is a simple question, but it has been given in a manner to confuse you. It's good to understand these kind of questions. So there's a block of mass m, mass 2 kg, which is pulled up on a smooth incline, means friction is equals to 0. The angle is 30° with the horizontal, and block moves with an acceleration of 1 meter per second square. And find the power delivered by the pulling force at a time 4 seconds after the motion starts. And what is the average power delivered during the 4 seconds after the motion starts? Now there is two concepts: power at 4 seconds and power average. Power average over 4 seconds. What is the difference between two? Are they both different? Are they both same? And is there something for work also? Work done at 4 seconds, or the work uh, done work average over 4 seconds? So here there can be concept of instantaneous power at some position. Whatever the work has been done, then we can calculate based on that, and we can calculate based on the velocity. We know that power is equals to force into velocity, and work is equals to force into distance. The difference here is that velocity can be instantaneous. Instantaneous velocity can be different, and hence power at different instance can be different. Power at different instances can be different, and we can have a different average power over the whole distance. However, no such concept exists for work, because work is dependent on distance traveled, and there is no instant distance. Distance is based on some, if you travel from here to here, then only you will be traveling a distance. So the work done will be same over the full. If in 4 seconds you traveled from A to B, so the work done at the instance, work done will always be from A to B, or from some point to some point. Hence there is nothing known as instantaneous work done. but there will be instantaneous power based on what will be the velocity at B. So this was one of the concepts which we needed to understand to get over this question. So once we understood this, now this thing will become easy. Now mass is 2 kilogram, theta is 30 degree from horizontal, acceleration is equals to 1 meter per second square, time is equals to 4 seconds, and we need to find power and all that. So first let's make the diagram. Suppose this is theta 30 degree with the horizontal, and the block is moving somewhat here. So it is pulled up on a smooth incline. A smooth incline means friction is zero, and since it is being pulled up means it will have some force this side. It will also have gravitational pull downwards, which will be mg cos theta in perpendicular to the motion direction, and parallel to the motion direction will be mg sin theta. And there will also be a normal reaction. Now same thing here, we can write it as, we can write in terms of the forces as F minus mg sin theta is equals to mass into acceleration. Now what is this F? We can write F is equals to mg sin theta plus ma, which is equals to m into g sin theta plus a, which is equals to m is 2 into g. For this let us say 9.8. Let us take g is equals to 9.8 meter per second square. Here 9.8 into sin theta. Sin theta is sin 30. Sin 30 is 1 by 2. And add it with acceleration. What is the acceleration? Acceleration is 1 meter per second square. So this whole thing comes as 11.8 Newton. So the force with which the block is being pulled up is 11.8 Newton. Now this is just the starting. Now we need to also find what is the velocity at time t is equals to 4 seconds. V at t is equals to 4 sec is equals to V is equals to at, which is equivalent to 1 meter per second square into 4, which is equivalent to 4 meter per second. So now power delivered by, we have the velocity at 4 meter per second. So power delivered at t is equals to 4 is equals to F bar into V bar. So F, we have F which is 11.8, and we have V which is 4 meter per second. So this whole thing becomes approximately is equals to 47 watt. Now this is power at t equals to 4. This is not the average power. Now in order to find the average power, as I told you earlier, for power we use F into V, and for average power we will calculate using the work by time, work over the total time, and that will be based on distance. So we need to find the distance traveled in 4 seconds is equals to half a t square. Now why is this half a t square? It is because we are using the equation of motion, which is s equals to ut plus half a t square. Here u, initially the velocity is 0, and also the block moves with a acceleration of 1 meter per second square, uniform acceleration. There is no friction, so acceleration is not stopped. So it is a uniform acceleration. So uniform acceleration, this is the equation. The initial velocity becomes 0. So we are using this half into a. A is 1 into t square. T square is 16. So this is 8 meters. Now work done at time t equals to 4 is f bar into distance traveled. So here f bar is 11.8. The force has remained constant. So and 8 meter it has traveled. So it comes to approximately 94.4 joule. So P average power delivered will be work done in 4 seconds by the total time taken. So work done by time taken is equals to 94.4 joule by 4 seconds, which is equivalent to 23.6 watt. So approximately 24 watt of average power is delivered, and instantaneous power at t equals to 4 is 47 watt. So using this question, we understood the difference between instantaneous power. We also understood that there cannot be instantaneous work because work is dependent on distance, and there can be power instantaneous and power average. So every question in HC Verma book leads you to some new concept. So you need to be very curious, you need to be very articulate, and you need to understand each and every concept which we are using in solving the questions. Now this is also a model of question where we use calculus to solve the work done. So it says that there is a force, some variable force. Up to now we were dealing with constant forces where the forces were constant. In the earlier example also, the force with which the block was being pulled up was a constant force. But here now the force is variable and it depends on 10 plus 0.5 x. X is the direction, particle in the x direction, and x in meter means x is the distance here, and F is in Newton here, force is in Newton. So what will be the work done by this variable force during displacement from x equals to 0 to 2 meters? Now we know that F is equals to 10 plus 0.5x. 10 plus 0.5x. So we can write that work done is equals to force into distance, traveled. So we can write it as 10 plus 0.5x into dx. So why I am using dw is because it is a variable force, and since we are going to integrate it, so first we need to find what is the small work done. The small work done for some smaller distances, f bar into dx bar, that is 10 plus 0.5x into dx. Now what will be the work done by this force? So work done by this force is equals to integration of this dw, and what is this work done by this force from x equals to 0 to 2 meter. So that is 0 to 2 meter. Now what is this dw? This dw is 10 plus 0.5x dx integration from 0 to 2, which is equivalent to, you can write it down as 10x plus 0.5 x square by 2. So and this thing is from 0 to 2. So if we put t, this becomes 20 plus 2 121 minus 0. So this whole thing becomes 0 is equals to, so this is equals to 21 joule. So that is, there will be variable forces question also, there will be constant forces question also, and there can be certain questions where a mix of both is working. So we have to work it accordingly. And one thing is to be kept in mind here is that if a variable forces, if a variable force acts, then we need to integrate. We need to understand when to use integration, when to use the direct formula, and that clarity of thought can only come after you solve questions. Now, this is a bit of a conceptual question. So, I mean, there is nothing numerical about it. It is just to brush up your concept, or to make you think it in a different way. So, suppose a body is dropped from a height h and it reaches the ground with a speed of 1.2 root gs. So, speed at ground is equals to 1.2 root gh. So, what does speed at ground means? It means if a body was dropped from a height h, it has reached the ground. When it reaches the ground, at the ground, the gravitational potential is equals to 0, and only kinetic energy remains, and we have the speed. So, and since we know that the total mechanical energy is conserved, which means that the sum of kinetic energy plus uh, potential energy knu is equals to constant. So here we can do k plus u, which is k is half mv square, half mv square. V square is 1.2 root gh whole square, plus, since potential is 0, which is equivalent to the work done. I mean, which is this constant. So this is w, and work done, or we can say total mechanical energy or whatever, uh, will be equals to 1.2 root g square half m, which will be 0.72 mgh, 0.72 mgh. Now up to here we know that this is total mechanical energy, or the work done, it is constant. Kinetic energy plus potential energy is constant. Up to here we know. Now what is the question asking us to do? The question is asking us to calculate the work done by air friction. How do we do that? Now, if a ball, suppose there is a ball and it comes down, so we know that it has certain velocity when it reaches the ground, but during its journey from here to here, from A, which is at a height h, from A, which is at a height h, to B, which is ground, which is h equals to 0, no height is here. So there will be some work done by air friction because friction is present here. What we will do? So will the total mechanical energy be conserved here? Here the work done by force of gravity. What will be the work done by force of gravity? So we know that at point A there will be some mgh potential energy, and we know that when it reaches down, at down, so this is work done at B. We know that work done at A, or the mechanical energy, or the energy at A, is equals to potential energy mgh height, and kinetic energy is 0 at this point. Kinetic energy at A is equals to 0 because there is no velocity. It is coming from rest, the body is dropped. So, and when only forces, the forces which are acting are gravity plus uh, friction by air, friction by air. So we can safely assume that the loss in this energy, or delta W, is equals to WB minus WA, which is equals to 0.72 mgh minus mgh, which is equivalent to minus 0.28 mgh. We can safely assume that this change in energy is due to the work done by air friction. Work done by air friction. Now this is a simple equation where it says that there is a block of mass m, and which is pulled along a horizontal surface by applying a force at an angle theta, with the horizontal, and friction coefficient between block and surface is mu. If block travels at uniform velocity, then find the work done by this applied force during a displacement d of the block. So what is it saying? It is saying that there is a horizontal surface on which is kept a block, and a force F is being used to pull it, and that is at an angle theta with the horizontal, and in the opposite direction frictional force is applicable, which is equals to mu into n, and in downward directions mg is applicable, upward directions normal reaction force is applicable. Now we can safely write that F cos theta is equals to mu n. This is F cos theta here, and component along vertical direction will be F sin theta. We can similarly write that this is equation 1, and similarly we can take the vertical component of F, which is F sin theta, plus normal reaction is equals to mg. So which gives us n is equals to mg minus F sin theta, which is equation 2. Now we have to work done by this applied force. Which applied force? This. So what we will do? We will do this. We will put 2 into 1. That will become F cos theta is equals to mu into normal reaction force, and normal reaction force is mg minus F sin theta. So this thing becomes F is equals to mu mg minus F sin theta by cos theta. F is equals to mu into mg minus F sin theta by cos theta. Now this thing, okay, sorry, here we have to equalize this. We have to calculate x for x. So we can write it as F cos theta is equals to, this implies that F cos theta is equals to mu mg minus mu F sin theta, and we can take F this side, so it becomes F cos theta plus mu F sin theta is equals to mu mg, which leads us to F into cos theta plus mu sin theta is equals to mu mg. So now F becomes mu mg by cos theta plus mu sin theta. Now this is what F is. So if we need to find work done by this, then work done by this force is work done is equals to F into D into cos theta, which is equivalent to mu mg by cos theta plus mu sin theta. This is F into D into cos theta, and this is the answer. We simply have to resolve the equation. We have to check for the forces and simply have to put it in the equation of the. Now this question is a little creative. So what does it say? It says that there is a two cylindrical vessel of equal cross-sectional area contains water. In one column it is up to H1, and another column and another vessel it is H2. So the vessels are interconnected so that the levels in them become equal. Calculate the work done by the force of gravity during this process. So let us see that there are two vessels, and these are the vessels. So just say that these vessels are interconnected. So one of them the height is h1. So here in one column the height is h1, and in another column the height is h2. Now suppose this was locked. Now when this gate was opened, when this is opened, what will happen? We know that the heights becomes equal. Both of them will come of the same height. So can we say that that same height at which the water will stop flowing from either side will be h1 plus h2 by 2. It is the average of both the heights. Suppose if this is at 10 meter and this is at 8 meter, then ultimately the 10 meter water will drop to 9 meter and 8 meter water will rise to 9 meter, and then it will stop. Think about it. This is a major concept for solving this question. Now, one another thing is that we know that mass is equals to density into volume. Now, water has a the same density this side also the same density, so we are not going to play with that. And we know that in the question it is given that equal cross-sectional area. It means that if we divide volume, then it will be area into length, or height. So area cross-sectional area is same, so rho A is same. So we can say that in H1 column mass is equals to rho A H1, and in H2 column mass is equals to rho A H2. So if the water which was in H1 column reaches this point, and this point is H1 plus H2 by 2, then it means that it has descended to this height. So what is this height? We can say that this small height L, we can write it as L is equals to H1 minus H1 plus H2 by 2, because this is the H1 plus H2 by 2 distance. This is H1, so this will drop in height will be that. So that mass, can we write that mass of this volume of water which descended, mass in column, suppose let us call it this A and let us call this B. So mass in column A, decline in mass of water in column A is equals to rho A into H1 minus H1 plus H2 by 2. which is equivalent to rho A H1 minus H2 by 2. And similarly in column B, what will be the mass raised? Similarly in column B, it will be raised by mass this small height. If let